Well, we can have a test for conservative vector fields in our cube. And if we let m, n, and p have continuous first partial derivatives on an open sphere Q, that's like kind of like an open disk, then the vector field given by f of x equals our m I plus our n, which is going to be a function of, actually this would be a vector field f of x by z, pardon my error there, n, function of x, y, and z, times j plus p, function of x, y, and z times k. It is conservative if and only if the curl of f of x, y, z is the zero vector. So in other words, f is conservative in space if and only if partial of p with respect to y is partial of n with respect to z, and the partial of p with respect to x is the partial of m with respect to z, and the partial of n with respect to x is the partial of m with respect to y. Now you're thinking, where does all that come from? And that comes from here. Actually, I'll even go before that. These things each have to be zero, so the curl of f of x, y, z can be the zero vector. So let's try one. Actually, two examples in this one. Determine whether or not f is conservative. If it is, find a potential function for f. And so our f of x, y, z is e to the z times y I plus x j plus 1 times k. So in other words, e to the z y I plus e to the z x j plus e to the z k. And so we've set up our curl determinant I, j, k in the front row, partial with respect to x, partial with respect to y, partial with respect to z. I know they're not numbers, they're operators, but bear with me, it works. So it's going to be I times the partial of this with respect to y, which is 0, minus the partial of this with respect to z, which is going to be x e to the z. So it's 0 minus x e to the z, I, and then minus j times the partial of this with respect to x, which is 0, times the partial of this with respect to z, which is y e to the z, and that was negative, and I, or the j in this position would be negative, so they cancel each other out and make a positive. And k times partial of this with respect to x, which would be e to the z, minus the partial of this one with respect to y, which would be e to the z. So e to the z minus e to the z is 0k. So we got negative x e to the z I plus y e to the z j, and really I didn't need to go that far. I just needed to show that this wasn't 0, because what we have in fact is that this is not the zero vector. Therefore, not conservative. But here's one that is. Determine whether or not f is conservative. If it is, find a potential function for f. So f of x, y, z, the vector field, 3x squared y squared z I plus 2x cubed y z j plus x cubed y squared k. And so we set up our curl equation. And so this goes here, this goes here, this goes here. Sorry, my highlighting is not working very well. I, j, k, and across the top, and then we do this. It's I times the partial of this one with respect to y. That would be 2x cubed y minus the partial of this one with respect to z, and you can see it's 2x cubed y, so we get 0i, minus j times the partial of this one with respect to x, which would be 3x squared y squared, minus, actually minus a negative, so we say plus the partial of this one with respect to z, 3x squared y squared, so, and again we get 0j, and then k times the partial of this one with respect to x, which would be 6x squared yz, minus the partial of this one with respect to y, which would be 6x squared yz. So again, we get 0. Okay, so it is a zero vector, therefore it is conservative. Now, if it is, then we need to find a potential function. Something that this is the partial with respect to x of, this is the partial with respect to y of, this is the partial with respect to z of. So, if this is the partial with respect to x of a function, we can find that function by integrating that dx, and we would get x cubed, the 3's would cancel, y squared and z are constant, so x cubed y squared z plus some constant function of y and z, because if we took the derivative of this part that only had y and z in it, with respect to x we get 0. So therefore, we can say, well, what about this is going to be the partial derivative of something with respect to y, and so we integrate this one with respect to y, we would get 2, no, actually the 2's would cancel because we're going to get y squared over 2, so we get x cubed y squared z plus some function of x and z. Similarly, we integrate this one with respect to z, and of course x squared and y squared is just a constant, so a constant times 1 dz is just x cubed y squared z plus some constant function of x and y. So the potential function is such that all these constants are the same. Well, the only way they could be equal is if they're just some constant c, because if this had an x in it, well, it couldn't have an x in it because it's a constant function of y and z, but if this had a y in it and a z in it, and this one, of course, well, couldn't have a y. This one couldn't have a z, so not possible. So our potential function is f of x, y, z is x cubed y squared z plus some arbitrary constant c that won't come into play if we found the partial derivatives. So, note the curl of a vector field is the self of vector. I think I mentioned that. So you can find the curl of f. And you could, for that matter, find the curl of 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 f. But it sure would be curly.